So by now we're pretty comfortable evaluating the sine, cosine, tangent, secant, cosecant, and cotangent of angles using the unit circle. However, one of the limitations of the unit circle is what we see. Well, we only get some of the special angles that are between 0 and 2 pi. So this brings the question to mind, what happens if we have angles that are greater than 2 pi? Or what about angles that are less than 2 pi radians? And in this video, we're going to study ways to help us evaluate trig functions of such angles. First off, let's look at a little bit about our function sine and cosine. What is the domain of the sine and cosine functions? Now remember, domain refers to our inputs. What are we able to take the sine and cosine of? And the answer is all real numbers. The domain of our sine and cosine functions is the set of all real numbers. There are no restrictions on the values that you can plug in for an angle theta. We can evaluate the sine or cosine of any angle out there. What is the range of the sine and cosine functions? Recall that range refers to the outputs of our function. What do we get out? And the range of the sine and cosine functions is from -1 to 1, including both of those endpoints. This set of numbers represents all the values of y and x on the unit circle. So again, think back to what your unit circle looks like. To evaluate the sine of an angle on the unit circle, you need to identify the y-coordinate. Well, the smallest y value that we have on the unit circle is -1, and the greatest y value that we have on the unit circle is +1. Therefore, we have to get out something between -1 and 1, between or equal to -1 and 1. Same thing for cosine. Cosine corresponds to the x-coordinate on the unit circle. And our greatest x-coordinate is 1. Our smallest x-coordinate is -1. Therefore, we have to get out some number that is between or equal to -1 and 1. What is the period of the sine and cosine functions? All right, here's a new term, period. This means how long does it take for the function to repeat itself? And in the case of sine and cosine, the period is 2 pi. This describes how frequently the function repeats. Notice that any multiple of 2 pi results in one complete revolution. All right, so hopefully that makes sense. Notice that if we have an angle that's going to be greater than 2 pi, if I complete 2 pi, I end up exactly where I started with on the unit circle. Same thing if I were to complete 4 pi or 6 pi or any other multiple of 2 pi. Those are all going to give us complete revolutions. So, a function f is periodic if there exists a positive real number c such that f of c plus x is equal to f of x for all x in the domain of f. The smallest number c for which f is periodic is called the period of the function. In the case of sine and cosine, the number c is 2 pi. We just said the period of sine and cosine is 2 pi. We can use the periodic nature of sine and cosine functions to help us evaluate trig functions of angles that are greater than 2 pi or less than -2 pi. The sine of 2 pi n plus x is equal to the sine of x when n is an integer, and the cosine of 2 pi n plus x is equal to the cosine of x where n is an integer. So what is this saying? Well, 2 pi n, any multiple of 2 pi where n is an integer, is going to result in complete revolutions, right? So this is how many complete revolutions are we doing, plus whatever else we are tacking on. And notice that again, a complete revolution will bring us back to where we started on the unit circle. Therefore, the sine of 2 pi n plus x is going to equal the sine of x. Same thing with cosine, right? This 2 pi n just refers to the number of complete revolutions plus whatever we are tacking on. Complete revolutions bring us exactly to our starting spot. Therefore, this entire quantity will be equal to the cosine of x itself. What's the best way to go about doing this? Well, when you guys are given your angles, rewrite fractions of pi as mixed numbers to allow you to determine how many complete revolutions are being made. So for example, here is an angle, 7 pi over 3. Now this angle is greater than 2 pi. Anytime you see angles that are written that are greater than 2 pi, it can be helpful to write them as a mixed number. So how many times does 3 go into 7? Well, it goes into 7 twice with a remainder of 1. This would be 2 and 1/3 pi. Notice in this case, we would have one complete revolution, and then we would be adding on a third of pi onto that. Let's see if we can't put it to use with some other angles here. Evaluate the trigonometric function using its period as an aid. Sine of 9 pi over 4. So we recognize right off the bat that 9 pi over 4 is greater than 2 pi. Whenever we see angles that are greater than 2 pi, rewrite the fraction as a mixed number. How many times does 4 go into 9? It goes in twice with a remainder of 1. Therefore, this is the same thing as 2 and 1/4 pi. Well, what is that saying? This is the sine of 2 pi plus 1/4 pi, right? That's what would give us 2 and 1/4 pi. 2 pi is one complete revolution. There's my 2 pi. And how much farther do I have to go? Well, I have to add on another quarter of pi. And there we have the angle 9 pi over 4. And the corresponding ordered pair associated with that angle would be root 2 over 2. So, to evaluate the sine of 9 pi over 4, well, that's going to be the exact same thing as the sine of the angle pi over 4. Notice that they terminate in the exact same location. And what's the sine of pi over 4? That's going to be equal to root 2 over 2. All right, so sine of 9 pi over 4 is equal to root 2 divided by 2. Let's try another one. The cosine of negative 5 pi. Well, in this case, we cannot write negative 5 pi as a mixed number, but we can still identify the number of complete revolutions. How many complete revolutions are we going to be doing here? 2 complete revolutions in the clockwise direction, and then we are going to have to continue for another pi radians in the clockwise direction. In other words, we have negative 4 pi minus pi. So what does that mean? Well, let's come over to our unit circle and let's count it out. Again, we start on the positive x-axis and we are going in the clockwise direction. There's negative 2 pi, negative 4 pi, and we have to continue another negative pi, bringing us to negative 5 pi. And the corresponding ordered pair is negative 1, 0. So what does this mean? Well, the cosine of negative 5 pi, that's the same thing as the cosine of negative pi, right? This negative 4 pi is just 2 complete revolutions in the clockwise direction. And what's the cosine of negative pi? Well, to evaluate cosine, we need to identify the x-coordinate, which is negative 1. All right, the sine of 15 pi over 2. Again, we have an angle, this being greater than 2 pi. So rewrite the fraction as a mixed number. How many times does 2 go into 15? Well, it goes in 7 times, and there's a remainder of 1. So sine of 15 pi over 2, that's the equivalent of the sine of 7.5 pi. So how many complete revolutions are we doing, and what do we have to add on after that? Well, that's going to be 3 complete revolutions from 6 pi, and then we're going to have to add on 1.5 pi, or 3 pi over 2. Notice 6 pi plus 1.5 pi gives us 7.5 pi. So 6 pi, that's 3 complete revolutions, and don't be afraid to count it out on your unit circle. Ready? We're going in the counterclockwise direction. 1 revolution is 2 pi, 4 pi, 6 pi, and now we must continue another 3 pi over 2, another 1.5 pi. All right, there we have our angle 15 pi over 2 and the corresponding ordered pair 0, negative 1. So what does this mean? The sine of 6 pi plus 3 pi over 2. Well, 6 pi is just a complete revolution, so we don't even have to worry about that. That's equal to the sine of 3 pi over 2. To evaluate the sine of 3 pi over 2, we need to look at the y-coordinate associated with that angle, which is negative 1. All right, let's try one more here. Evaluate the trigonometric function using its period as an aid, the cosine of negative 19 pi over 6. Again, here I have an angle that is less than negative 2 pi. So I'm going to be going through greater than one complete revolution in the clockwise direction. How many times does 6 go into 19? Well, 6 goes into 19 three times with a remainder of 1. So this is the same thing as the cosine of negative 3 and 1/6 pi. So how many complete revolutions are we doing and how much farther do we have to travel? Well, this would be negative 2 pi minus 7/6 pi. Notice negative 2 negative 2 minus 1 and 1/6 gives us negative 3 and 1/6 pi. So because this negative 2 pi is a complete revolution, bringing us back to where we started, we don't really even have to worry about it. Okay? How much farther do we have to travel though? Negative 7/6 of pi. All right, traveling negative 7/6 of pi brings us to here for our angle. And the corresponding ordered pair is negative root 3 over 2, comma 1/2. So we can say that the cosine of negative 2 pi minus 7 pi over 6 is equal to the cosine of negative 7 pi over 6. Again, negative pi over 2 brings us exactly back to where we started, so we don't even have to worry about it because of the period of our function. All right, and cosine, we need to identify the corresponding x-coordinate, which is negative root 3 over 2. And there you have it. Evaluating trig functions of angles that are greater than 2 pi or less than negative 2 pi using the unit circle. What it comes down to, rewriting your fractions as mixed numbers and again, just counting out to where you have to go. Figure out how many complete revolutions you are doing and what you have to tack on after that.